We saw suffix tries, and we saw that suffix tries are too big, which is to say the number of nodes of the suffix trie generally grow quadratically with the length of the input string. We would instead like to have a radically slower rate of growth of the index data structure with respect to the text. So let's make our way that way, starting from the suffix trie and trying to reduce the amount of space that we're using to represent that suffix trie. So I should say reducing the amount of space that we're using to represent the suffixes. Okay? All right. So here's what we saw with respect to the suffix trie. Suffix tries, in terms of the number of nodes in the trie, grow pretty strongly quadratically with the length of the string. If you believe that this is a realistic example, this was an example using a genome sequence from a virus and taking longer and longer prefixes and asking how many nodes are in the suffix trie, and the answer is the number of nodes is quite close to the worst case. That's bad enough that if we wanted to apply this data structure to the human genome, it would be unrealistic, so we need to make it smaller. Okay, so how do we make it smaller? So here's a picture of our suffix trie of the string ABA, ABA, and one thing that we might notice, if we want to make this thing smaller purely in terms of the number of nodes and edges in the thing, let's just focus on one sort of subtree of this larger tree for the moment. We can see that some of the branching structure here is trivial, right? So like this chain here is just a chain of, this node has one parent and one child, one parent, one child, right? These nodes in the middle are, in some sense, useless, right? They don't actually represent any interesting branching. So what if we were to just sort of coalesce them, right? So let me use orange here to represent a sequence of labels of edges in that straight line portion of the trie. What if we were to just collapse them and end up with something that looks like just 3 nodes? This path here would stay exactly the same, right? So this path is still $, and this is still a leaf. But now this one on the left, we just have one edge, and we have to give it a string label. AB, $. Right? So you can see what I did. I just concatenated the original edge labels, and I gave this new coalesced edge a string label consisting of all of them concatenated together. Okay. So that's my first idea that I can apply. And you can see that the sense in which it is making the data structure smaller is particular, right? It's making sure it has fewer nodes and edges. In this example, we got rid of 3 nodes and 3 edges. Right? This has 3 fewer nodes and 3 fewer edges compared to this subtree of the suffix trie on the left here. Okay, so that's our first idea. And even this first idea is actually kind of profound. It's already going to accomplish quite a lot for us. So let's see what exactly it does accomplish. Well, we know it reduces the number of nodes and edges. And another thing it does is it creates, if we were to do it everywhere, so if we were to apply this idea absolutely everywhere where we saw a trivial chain of nodes in the trie, then we would have a new guarantee when we were done. Our guarantee would be that all the non-leaf nodes of this newly coalesced version of the suffix trie have, right, ... they have something is the case about the number of children that they have. And the answer is they have at least one, or I'm sorry, more than one child, so at least 2 children. Okay? It's right there in the nature of the coalescing that we're doing, that when we're coalescing away nodes that have exactly 1 child, right? Nodes that have exactly 1 child are the ones we're getting rid of when we do the coalescing. And so when the coalescing's done, we're left with leaves and non-leaves that have at least 2 children. Right? They can't have 1. So we're left with leaves and non-leaves that have at least 2 children. So let's actually do this process for this entire trie. To help me along, I'm just going to use some coloring here. All right, so I'm coloring in the edges that are going to be coalesced away and sort of like merged in with the edge just below. Right? So those are the edges that are going to go away. The destinations of those edges are the nodes that have one child. All right, so when I'm finished coalescing, I guess what I'm going to get is going to look something like this. There's my root. I'm still going to have this $sign off to the right. Okay, great. To the left, I still have my edge labeled A, right? So that just moved this edge over. Let's now work on this path here, coming down from that node. So now I'm going to coalesce that down to just one edge. Okay, and the label for that edge is going to be $, and I'm going to use blue to represent the characters that came from those edges that we coalesced away. Okay, so there we go, $. Right, so that is a coalesced version of that. Okay, let's keep going. So let's do this bit right here. So there's a little bit of coalescing going on here. So there's a new edge coming down here. That edge is going to be labeled B, which got coalesced away. Used to be an edge label that got coalesced away. BA, right? BA. I'll put that third one in as long as I'm here. This is the $sign points to a node here. Okay, so far so good. Now let's finish off this subtree. It's got 2 children, 1 child. This is just like we were seeing before. $. Use green ABA $leaf, and then $leaf. Okay? Great. So I've now got this entire subtree taken care of. So now what's left is this subtree here. So let's do this chain here, BA, the B in red, so the B gets coalesced away, A, to this node. That node now has 2 children. One where the label is this coalesced path, so ABA $. I'll use orange, ABA $, and then the other is just $. Okay? There we go. So that what you have on the right is just a version of what you have on the left, but maximally coalescing, doing all that coalescing. And let's just pretty up the picture a bit. Okay? All right, and recall that we said that this coalesced version of the tree, I'm going to stop calling it a trie because it's not a trie anymore because the edges don't have character labels anymore, which was one of our requirements when we defined the trie. So the thing on the right is not really a trie. It's coming closer to something that we're going to call the suffix tree. So I'll just call it a tree. So this tree on the right has the property that we said it would, which is to say it's got leaves, and then the non-leaves have at least 2 children. Right? So this has 3 children. This has 3 children, 2 children, 2 children, and those are the non-leaves. Okay? So it does have that property we said. Okay, so obviously we reduced the number of nodes and edges on the right. In fact, let me color in the nodes on the right and show basically which nodes on the left they correspond to. So the ones on the left that are colored gray are sort of like the ones that survived when we did the coalescing, and then the ones that are not filled gray are the ones that got coalesced away when we did the coalescing. So the ones that are non-gray on the left are the ones that have exactly 1 child, and on the right they're gone. Right? So all that's left are nodes that have more than 1 child, leaves and non-leaves that have more than 1 child. Okay, so we can make an important observation about what happens to the total number of nodes in the tree when this property holds. So when we have the property that no node has an only child, in other words, nodes are either leaves or they have 2 or more children. So no nodes have an only child. If no node has an only child, then we can bound the total number of nodes in the tree in terms of the number of leaves, m. Okay, so what is this bound that we can apply? Okay, well, it helps to start with a different kind of tree, specifically a binary tree. So in a binary tree, This is a tree where the non-leaves have exactly 2 children. Right? That's a little bit more specific than the kind of tree that we're talking about, but that's okay because we can get from this kind of tree to our kind of tree in our argument. But in a binary tree, the number of leaves and the number of non-leaves are very clearly related because the number of non-leaves is just the number of leaves minus 1. Right? So if the number of leaves is m, in this example that's 8, right? So if the number of leaves is 8, then the number of non-leaves, which are the blue things in this diagram, is m minus 1, which is to say 7. So there should be 7 non-leaves in this diagram, and there they are. Okay? Now that's with a binary tree, so in other words, a tree where there are leaves and then there are nodes that have exactly 2 children. The kind of trees we're talking about are trees that have leaves and then they have nodes that have at least 2 children. So it doesn't have to look like this. It can look, like we could add a little bit onto this. Like, for example, if we allow some of these non-leaves now to have more than 2 children, like, for example, maybe we add on an extra child over here so that now this node has 3 children. Well, that added a leaf. So now we have 9 instead of 8. But it didn't add any non-leaves, right? So we actually made that, whereas before the number of leaves was m, the number of non-leaves was m minus 1. Now they're getting farther apart. So if the number of leaves is m, the number of non-leaves in this case is m minus 2. So they're sort of moving potentially farther apart, right? And if we just explore one other way that we could augment this graph or this tree so that now we have more nodes that have more than 2 children. So now this node has 3 children, and then I added this little subtree here. Now we have 11 leaf nodes and we have 8 non-leaf nodes, right? So they're getting even farther apart. What it speaks to is that in the kind of tree we are talking about, the kind where the non-leaf nodes have at least 2 children, the number of leaves bounds the number of non-leaves. Specifically, if the number of leaves is m, then the number of non-leaf nodes has to be at most m minus 1. At most m minus 1. It might be less than m minus 1, but it is at most m minus 1. Okay, if it's a binary tree, then it's exactly m minus 1. But if it's our kind of tree where in general we might have some non-leaf nodes that have more than 2 children, then it is at most m minus 1. Okay, let's call this the no only child principle. That if we have no only children in our tree, in other words, we have a tree consisting of leaves and then non-leaves that have 2 or more children, then the number of non-leaves is at most the number of leaves minus 1. Okay? And this is a property that our new tree has, the tree that we get if we start with the suffix trie and then do all the coalescing. All right, so there's the no only child principle tells us this. If we add them together, of course, now we have that the total number of leaves is at most 2m minus 1. Right, I just added these two things together. So the total number of leaves is at most 2m minus 1, but that means that the total number of leaves is growing linearly with m. Right, that function, 2m minus 1, is linear with respect to m. In other words, it's big O of m. So this is a big deal, right? Because we were just criticizing the suffix trie because the number of nodes was growing quadratically with the length of the suffixes. We even came up with examples where the where the strings were really simple, but still the number of nodes was growing quadratically with the number of characters. But as soon as we apply this trick where we do all the coalescing, get rid of all the nodes that have exactly 1 child and make a new tree where the edged labels could be strings, as soon as we do that, we have a brand new, excellent guarantee on how many nodes there are in the resulting tree. There are big O of m nodes. There's at most 2m minus 1, where m is the number of suffixes in our text. Okay? So that's actually a big improvement over the suffix trie. So we may be feeling like we want to declare victory, but we cannot quite yet, right? There is actually, so this is nice, but the total space is not yet big O of m. The total space is not yet big O of m. Why is it that the total space represented here in this data structure, required to store this thing that I'm showing here, why is it that that is not big O of m? Well, because if you look at the edge labels, which are now allowed to be strings, right now that we've coalesced, these edge labels, the total number of characters in all those edge labels is still growing just like the suffix trie did, right? The total number of characters in the edge labels is growing with the total number of characters in all the suffixes after we've done the prefix, after we've collapsed shared prefixes, right? So it's actually exactly the same as the number of, the number of edges in the suffix trie. So however the suffix trie was growing, it should be the same as that. The same as that is the rate of growth of the total length of all these edge labels, okay? So we can't claim that this thing shown here in this picture is a data structure whose overall size is growing with big O of m. We can claim that the number of nodes and edges grow with big O of m, but we cannot claim that the total size grows with big O of m, right? The total length of the edge labels is still growing, worst case, quadratically. So we have to solve that problem too. Okay, so here's an idea for how to solve that problem. Notice that all of the labels on all of the edges are substrings of t, right? All of the labels on all of the edges here are substrings of t, which means that if we keep t around, right? If we keep t itself, the string t, then we don't need to copy those substrings of t into the edges of this data structure so that we are literally keeping these copies of those substrings here as the edge labels. We can instead put on the edge labels a kind of reference to that substring, right? So sort of like a pointer into t, saying, okay, the substring labeling this edge is the substring here with respect to t, right? And it's not enough to just point to one spot. We actually have to have a pointer and a length, right? Because the substring, right, it could be of length 1 or it could be of length 4. We need to be able to represent how long the substring is that we are using to label our edge. So the idea is we're just going to take all these over here, all these substrings labeling the edges, and turn them in each case into a pair of numbers, an offset and a length with respect to t. So here's t down here. We're going to keep t around, and these edge labels are going to become offset length pairs with respect to t. So for example, let's just look at this edge, right? Its label is a. So let's just pretend for a moment that we're going to use that a as our edge label. So it's at offset 0. I'll use 0-based offsets. So that a is at offset 0. The substring in question is just a, right? So it just has length 1. And so we would put that as the edge label on that edge, 0, 1. That a is going to be encoded using that a, which is the a at offset 0. Sorry, I should say it's the substring at offset 0 of length 1. Okay? All right, well, let's keep going. Let's look at this ABA dollar here. Well, that corresponds to this substring of t, right? And that's the substring at offset 3. We're using 0-based offsets. So 0, 1, 2, 3. That starts at offset 3 and has length 4. So we'll put 3, 4 on that edge as its label. Okay? So that's the idea. If we do this for every edge, we might get a picture that looks like this. So now our data structure consists of this tree, which has big O of m nodes, big O of m edges, this text, which we're going to keep, which obviously has m characters, and then for every edge we have a label consisting of 2 integers. 2 integers. In other words, a constant number of integers, just 2 integers per edge. And so with that, the total space is now big O of m. We need big O of m things, let's say machine words, in order to represent this suffix tree data structure. Okay, it is now a suffix tree. We've now made it all the way to the point where we can call this thing on the right a suffix tree. Okay, and again, why is the total space now big O of m? Because the number of nodes is big O of m, the number of edges is big O of m, the length of the text is m. the total number of integers needed on all these edge labels is big O of m integers. There's one more important thing I need to say about the tree, which is to say, whereas in this picture I'm showing the leaves, using a circle just like all the rest of the nodes, the reality is that the leaves actually need to hold a little bit of information. We need the leaves to tell us which suffix that is that corresponds to that leaf. In other words, what's the offset of the suffix that corresponds to that leaf. So the last thing we need to do is fill in. I'm going to turn these into boxes now, and we're going to write numbers in these boxes corresponding to which suffix is it in each of those leaves. Okay. All right. So let's see. This suffix here, right? So if I draw this suffix here, is a length 5 suffix. How do I know that? Because the second number in these two edge labels is the length of the substring in question. Right, so this is a length 1 substring, length 4 substring, so the whole thing is a length 5 suffix. All right, so there's a total of 7 characters, so the length 5 suffix must be the one that occurs at offset 7 minus 5 equals 2. So I must have to put a 2 in this box here. Okay, likewise, let's do another one. This suffix, that one, has a length 1 plus 2 plus 4, so that actually has length 7. That's the longest of all the suffixes. So that's the one, meant to make that a 7. That's the one at offset 0, so I'm going to put a 0 in for that suffix there. Okay, let's do one more. This suffix, boom, 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 has length 4, right? So what am I going to put in that? I'm going to put 3, etc. Right, so in each of those leaves, I'm going to write the offset of the suffix that corresponds to that leaf. That's going to be useful, as we'll see. So that's just one last piece. Okay, so there's the complete picture of the suffix tree for this text. Let me just re-emphasize that in order for us to be able to work with these edge labels, we need to keep t. T can't be discarded, because to figure out what this substring even is, 3, 4, we need to be able to look up 3, 4 in t, right? So t is part of our index data structure. We can't throw it away. So the next thing I want to describe is the notion of a label. We already saw the notion of a label before with respect to the suffix trie, so this is perhaps review. But let's just say we're going to use the same exact notion of label as we used before. In other words, the label of a node is the string that would be spelled out if you concatenated the edge labels of the edges that you would cross going from the root to that node. So in this particular example, the edges that we would cross going from the root to this node are, this one's labeled A, this one's labeled ABA $, so we would concatenate them and get AABA $. So same notion of label, right? Nodes still have labels just like they did with the suffix trie, and it's the same exact notion. The notion of depth now is a little bit more confusing. There's two different kinds of depth that we could be talking about. One that kind of corresponds to the depth in this new tree, the node depth in this new tree, and the other that corresponds more to the notion of depth that we had before with the suffix trie. And so I'm going to distinguish them. I'm going to give them different names. We can talk about the node depth, right? So that's just purely the depth in terms of how many edges would I have to cross to get to that node starting at the root. So this would be at depth 0. These would be at depth 1. These would be at depth 2. These would be at depth 3. And then label depth corresponds to the depth as in how long is its label. Right? For a given node, we just saw that this node has label length 5. So this node is at label depth 5. Okay? So to take one example, this node here is at node depth 2 because 1, 2, we have to traverse two edges, to get to that node from the root. But it is at label depth 6, as we can see, because we would have to concatenate a string of length 2 with a string of length 4 to get its label. So it's at label depth 6. Okay, so let's ask the same question about the suffix tree as we asked about the suffix trie, because we said the suffix trie had a sort of unfortunate quadratic scaling characteristic in theory. But then we wanted to look at what would actually happen in practice if we built suffix tries of successively longer prefixes of a viral genome sequence. Now we know the suffix tree is going to be much better because we know that its size is linear in M. It's big O of M size. So we know it's definitely going to be better. But we can still ask the question, how close is it to the best versus the worst case? Right? So the best case, I suppose, would be the case where even though we know we have M leaves, we might not have very many non-leaves. So I suppose M, right, M leaves with no non-leaves is a pretty good case, right? Like that would be the case where we don't have we have close to the fewest number of internal nodes possible. Whereas, now that we know that the most number of internal nodes possible is M minus 1, the number of leaves minus 1, therefore we can't have 2M or more leaves in the whole tree. So that's like an upper bound, right? So we have sort of a linear lower bound and a linear upper bound. And if we were to actually build a suffix tree, we might ask, well, what do we actually see in terms of the number of nodes in that tree? And just like before, we could say, we could have the optimist's theory. The optimist's theory would be, I'm only slightly above the blue line. We could have the pessimist's theory. The pessimist's theory is I'm only slightly below the orange line. Or we could have a sort of middle of the road theory, whereby the suffix tree is growing at a sort of compromise, maybe halfway between best possible and worst possible rate. Okay, so in this particular example, what do we find? It's kind of that in-between one, right? The actual growth of this suffix tree in terms of the number of nodes in the suffix tree, it's not hugging either line. It's not very close to the blue line. It's not very close to the orange line. Maybe it's somewhat closer to the orange line. In other words, somewhat closer to the worst case. But I would call this a sort of compromise. It's sort of in between the smallest and largest possible number of nodes. Okay? But, crucially, it's way smaller than the suffix trie in terms of the number of nodes. Just look at the scale of this plot. Right? This plot only goes up to 1,000, and actually this highest point that we see here, I guess, is closer to 800 or so. Whereas before, when we made the plot for the suffix trie, we were seeing over 100,000 nodes in our suffix trie for the exact same data, the exact same virus sequence. Right? So much better, much more practical. Okay? So we've achieved something really amazing just with those two simple rules about how we can start with the suffix trie and make it smaller. We can coalesce the non-branching paths, get rid of those nodes that have exactly one children, and then we can change our strategy for how to label the edges so that we're labeling them with pairs of integers, where those pairs of integers are offset length pairs referring back to the string t. And now we have a much more practical data structure.